Hi there, and welcome to this lesson on Pure Mathematics 1. And in this lesson, we'll be looking at how you do differentiation from first principles. Now, when you actually do differentiation in A-level or in any other course in mathematics, you don't have to do what we're doing in this lesson, but this lesson will explain why differentiation works, where it comes from. Now, in the last lesson, we considered the curve y equals x cubed minus x squared minus 6x. And we considered the point a, 2 minus 8. And what we noted was that the gradient of the curve at a is exactly the same thing as the gradient of the tangent that you would draw at the point a. We then considered a point b close to a. And we drew the line between a and b. And we said that if b was close to a, then this green line would be close to the black line. So the line through AB would be close to the tangent at A. As you can see at this moment, it isn't that close. But we calculated the gradient of that line, and then we moved B closer to A. And as you move B closer to A, you'll notice that the green line gradually gets closer and closer to the tangent, the closer that you get to A. Now, the end of this process is when B actually reaches A, and you have the tangent at A. This process is what's called differentiation. Now, let's have a look at how this works out in practice. So let's say we had the same curve, y equals x cubed minus x squared minus 6x, and we wanted to find the gradient at any point whatsoever on the curve. So we'll try and do that, and then once we've got a method for doing that, we'll actually work out what the gradient is at this point, 2 minus 8. But we begin by just choosing 2 points on the curve, 2 general points. So the point at A, which is the one we're really interested in, we just call xy, the general value x, the general value y. And the point B, which is a little bit further away, we'll call x1, y1. Where x1 is equal to x plus some small amount h. So h is this distance here. It's the x distance between the two x values. Now the gradient of the line AB is the same as always. It's the change in y divided by the change in x. But what we would like to do is work out all of these 4 things in terms of x. Now, x just is x, so we don't have to do anything with that. x1, we can easily write that in terms of x because it's x plus h. That's how we defined it. Y is also easy to do. Y is already written in terms of x in the original equation. It's x cubed minus x squared minus 6x. So y1, that's the only point that requires a little bit of work. Now, what does y1 equal? Well, you'd substitute x1 into the equation. So y1 is equal to x1 cubed minus x1 squared minus 6x1. But we know what x1 equals. x1 is equal to x plus h. So we can substitute x plus h in for all of these values of x1. And that'll give us this. Then we multiply out the brackets. Multiplying out the brackets will give you all of these terms. Tidying things up a little bit will give us that. Now the gradient of AB, this is what we said it is, but we now know all of those 4 things. We know what y1 is in terms of x, we know y, we know x1, we know x. We can substitute all 4 things into the formula for the gradient. And that will give this long expression, where y1 is this long expression here. Take away y, which is what we have here. And on the bottom, we've got x1, which is just x plus h. Take away x. Now, a lot of things cancel straight away. The x cubed here cancels with the x cubed there. So do the x squareds. So does the minus 6x. And on the bottom, the x's cancel with each other. So the whole thing quickly simplifies to that. All of those terms on the top have a h in them. So we can divide by h. And when we do so, that is what we get. Okay, so what have we done? We've got a curve. By working out the gradient between any 2 points on the curve, we've got a formula for the gradient of the curve. And the formula is this. it'll be 3x squared plus 3hx plus h squared minus 2x minus h minus 6. Now what that'll give us is the gradient of this line AB. What we're interested in is what happens as B gets closer and closer to A until it's actually on top of A, and they're the same point. Now in formal mathematical language, this is what we're doing. The gradient of the tangent at A is what happens when B reaches A. Well, B will reach A when h becomes equal to 0. And the way we write that down is we say it's equal to the limit as h tends towards 0 of this expression. And as h tends towards 0, we'll get closer and closer to the gradient. And the limit is what happens when you actually arrive there, when h is equal to 0. Well, that limit is easy to work out. All you have to do is put h equals 0 into this expression up here. And this term vanishes, this term vanishes, and this term vanishes. And all you're left with is the terms that don't have h in at all. So the gradient of the tangent at A is equal to 3x squared minus 2x minus 6. And that's for any point on the curve. So what you have there is a formula that you could use to work out the gradient at any single point just by substituting in the value of x. Now the gradient of the tangent, as we said, that's the gradient of the curve. So when you're finding the gradient of the tangent, you are also finding the gradient of the curve at any point. And the point we were interested in was the point P2 minus 8. The significant number there is the x, because that's the only number we need to substitute in. So substituting x equals 2 into this gives us 3 times 2 squared minus 2 times 2 minus 6, which is 12, take away 4, take away 6, which means the gradient at this point will be equal to 2. Okay, that is differentiation from first principles. That's the process that you use. Now, a little bit on the language that you're likely to meet. So as we said, the gradient of the tangent today is written down in these terms. Very formal mathematical language, and the way you'd read it is the limit as h tends to 0 of 3x squared plus 3hx plus h squared minus 2x minus h minus 6. In general, if we have any function, y is f of x, then the gradient of the curve is equal to this limit. It's the limit as h tends towards 0 of the value of the function at x plus h, that was like y1 in the example we just did. Take away the value of the function at x, that's y in the example that we just did, and you divide that by h. So the gradient of the curve will be the limit of this expression. Now frequently, h is written as the Greek letter delta times by x. Now both h and delta x mean the same thing. They both just mean what's the change in x, how much has x changed by. And both of them are implying that it's a small amount, a small value. You also may see the following language, that the gradient of the curve of f of x is equal to the limit as delta x tends towards 0 of delta y over delta x. Now, this is the same letter as this letter here. They're both the Greek letter D. That's the lowercase version of the letter, and that's the uppercase version of the letter. Or, in terms of the lowercase thing, you'll frequently see this written in textbooks, that the gradient of the curve is equal to the limit, again, as delta x tends towards 0, of delta y divided by delta x. And these Greek letter Ds, so the capital D, the lowercase d, they are what become dy by dx in the formal language for differentiation. So the gradient of the curve f of x is equal to dy by dx. And the way you would read that, you can just read it as dy by dx, obviously, or that says that you are differentiating y with respect to x. And the final thing you might meet is function language, where if you have the gradient of the curve of f of x, staying in function language, you'll see that written as f dashed of x or f prime x. Okay, that gets us to the end of this lesson. If you've got the textbook, then turn to page 156 and have a go at exercise 8B. Thanks very much for listening, and cheerio.